So today we're going to talk about special right triangles. Yesterday we talked about right triangles, right, and Pythagorean theorem. We talked about the legs and the hypotenuse. And today it's special right triangles. And these, I don't know if they're so much special as they are simply triangles that we use a lot. They're triangles that we see often enough that it's worth it to us to remember some things about them. Okay, so I'm gonna go backwards here from normal. I think I'm going to start off with what we call a 45, 45, 90 triangle. So we're going to talk about a 45, 45, 90 triangle. Okay, it comes when we have a square I guess I should mark the sides congruent as well. If I draw a diagonal of a square, okay, so if I draw the diagonal of a square in, I have two 45, 45, 90 triangles. And I'm just going to draw one of them over here separately for us. Okay, so things we want to remember about. Now you can see, we're going to see this a lot. Okay, if you're an architect or an engineer or in construction at all, whatever that is, you're going to see a 45, 45, 90 triangle often. Okay, and so just looking at it for a second, what can you guys tell me about the legs of any 45, 45, 90 triangle? Yeah, they're congruent. It's an isosceles triangle, and often, okay, often we're not told. So we'll get something like this. We're not told that it's a 45, 45, 90 triangle. Often, what we're given is something like this, where we're given an isosceles right triangle. Okay, so every single 45, 45, 90 triangle, first of all, it's an isosceles triangle. So the legs are always the same length, aren't they? Okay, so if you know one, you know the other one. All right, so let's just draw one down here. So if I give you something like this, let's say I just tell you that one of the legs is 1 unit long. We'll just make it simple, okay? One leg is 1 unit long. Well, oh, sorry. Got it now? Okay. How long is the other leg? There you go. Okay. What about the hypotenuse? Can you guys figure out how long the hypotenuse is? What would it be? 1 squared plus 1 squared equals c squared. So what's 1 squared? So 1 plus 1 equals c squared. So 2. So how long is c? Okay, square root of 2. I think you guys were all like trying to figure out what the square root of 2 is in your head or on a calculator instead of just saying it's the square root of 2. Can we just go with that? Okay, so it's the square root of 2 units long. Now every single 45, 45, 90 triangle has this relationship where the legs are the same length and then the hypotenuse is the square root of 2 times the leg. So if this weren't a 1, let's say these were 4s, okay? If these were each 4s, we would get 4 times the square root of 2 for the length of the hypotenuse. Do you believe me? I don't know if you believe me. Here. Okay, so 45, 45, 90 triangle. A lot of times that's all we'll be given. You just have to understand what's going on. Let's say these are 4. Well, I say then the hypotenuse is going to be 4 radical 2. It's going to be radical 2 times whatever the leg is. What do you think? Zach, are you believing me? Okay. So tell me how to find C right there. Everyone happy? Now what? Square them. Add them up. Take the square root of both sides. Okay, now radical 32 is 2 times radical 2 times radical 2 times radical 2 times radical 2. I believe it's 5 2's multiplied together, isn't it? Try it. 2, 4, 8, 16, 32. 5 of them? Okay. So everybody, what's radical 2 times radical 2? Wait. It's radical 4, which is 2. And radical 2 times radical 2 is 2. And radical 2. And 2 times 2? 4 radical 2. Okay? So it is. It's 4 radical 2. So whatever the leg is, the hypotenuse is always whatever the leg is times radical 2. So this one would be 1 radical 2. And so in general, this is the good bit. Okay? That you really need to have on your notes. In general, if we have a 45, 45, 90 triangle, okay, and the leg is X, what's the other leg? X. And what's the hypotenuse? X radical 2. Now, technically, I should write that radical 2 times X, but I'm going to write it this way just for convenience, okay? So it's the leg times radical 2. It's always going to be that way. Okay. So next time you see a isosceles right triangle and you know how long one of the legs is, are you going to know how long the other leg is? And are you going to know how long the hypotenuse is? What is it? Yeah, it's 3 radical 2. And that's worth it for us to know it. Now, we could use the Pythagorean theorem every single time on a 45, 45, 90. Okay? We could use the Pythagorean theorem every time, but it's just worth it to know that it's radical 2 times the leg. Now, let me make life a little bit more difficult for you. Here's a 45, 45, 90. The hypotenuse is 6. How long's the leg? How are you going to find the length of this leg right here? Don't make it too hard. If I know the leg, how do I get the hypotenuse? If we know the leg, how do we get the hypotenuse? Not one of you, everybody. Times by radical 2. If we know the hypotenuse, how do we get the leg? Okay. Now, that's simple. You divide by radical 2. Easton, you got that? Simple, 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 right? There is a little bit of a problem, though, with this particular fraction. It's kind of like writing 6/8. Would you guys ever tell me at the end of an equation or for the length of the side of something that it's 6/8 inches or something like that? Carly, what would you do? Everyone agree? We're all okay? This is the same way. It's not reduced completely, and here's the problem. we can't write a fraction, okay, at the end when we're done with it, with the radical in the denominator. We just don't like that. It just makes life really difficult, okay? So we never write that radical. We never leave the answer like this. What did you say, Michael?
Can you leave the radical in the numerator?
So what we can do is I can get rid of the radical in the denominator by multiplying by radical 2. So whatever it is, if I multiply by it, what's radical 2 times radical 2? How come only one of you knew that? What's radical 2 times radical 2? Okay. Okay, so that's better. We don't have radical 2 in the denominator anymore. But Cordell knows if I multiply the bottom of a fraction by radical 2, what do I have to do to the top? I've got to multiply it by radical 2. See? So that we're actually multiplying by 1, right? Okay. So 6 times radical 2 is just 6 radical 2. Now, I know that this answer looks worse, okay, but technically it's simplified. So 6 radical 2 over 2 is the way we're going to give our answer. Okay? So on your paper there, let's say we have this. You don't need to draw the triangle or anything. Let's just say I have this triangle and I have well, let's just make this simple. This is 12. Can you guys tell me about the length of the leg? Don't go all the way. Just tell me the basic one. Okay. 12 over radical 2. Okay, are we going to leave the answer like that? No. We're going to multiply the bottom of the fraction by radical 2. We're going to multiply the top of the fraction by radical 2. And we get 12 radical 2 over what? 2. Now, I got to say, though, the one we just did, which is upside down right here, and this one right here, I'm still not going to leave the answer that way. I can still make it better. Who can see it? Who can see it? Yes?
Wouldn't it just be 2 divided by 12?
12 divided by 2? What is that? 6 radical 2. What about this one over here that we did before? 6 radical 2 over 2, what's that going to be?
3 radical 2.
Yeah, 3 radical 2. So it's just a matter of simplifying it down, okay? So does everybody have this in their notes? Okay, so that's our first special right triangle, 45, 45, 90. The other special right triangle, the other one that we see enough that it makes it worthwhile to memorize some stuff, is called a 30, 60, 90 triangle. 30, 60, 90. Oftentimes, you'll only be given one of these. This one's 30, that's a right triangle, and you need to see, oh, that's a 30, 60, 90, or maybe it'll give it to us like this. Okay? It's not an isosceles triangle, is it? Okay? But there is some relationship here, okay? And the first thing is, I'm just going to start off with this leg right here. I'm going to call it the short leg. In every 30, 60, 90 triangle, there's a short leg. And we're going to base everything off of that. We're going to say that's x, okay? And the hypotenuse is always double. Every single time, every 30, 60, 90 triangle, the hypotenuse is always twice as long as the short leg. Who's seen this before? Anybody? Actually teaching you something new. Fantastic. Okay. So that's the start of it, okay? And the long leg, again, we're going to base it off the short leg. Okay, we always come from the short leg. The long leg is radical 3 times the short leg, which I shouldn't write it that way. I should write radical 3x, but usually we have this number and we just have to multiply that number by radical 3. So this is the deal with every 30, 60, 90 triangle. So even if the triangle's smaller, if it's a 30, 60, 90, it's similar. Every 30, 60, 90 triangle is similar to every other one, okay? And that means that the relationship between the short leg and the hypotenuse and the long leg is always going to be the same. So in here, if the short leg here is y, how long is the hypotenuse going to be, guys? 2y. And how long is the long leg going to be? Yep. I'm going to say y times radical 3. It's always going to be that way. If I have a big old honkin' 30, 60, 90, woo, okay? Let's go a little different direction this time. Let's say the hypotenuse is 10 units. Short leg's 5. Now you're never going to go from the hypotenuse to the long leg. You kind of have to work your way around. We don't really memorize how this works, this direction, but we know the short leg's half. And then you can take the short leg, multiply it by radical 3, and there's the long leg. Okay? Should I show you the hard one? Yeah. This is the bad one. When I give you the long leg. Okay, if you know the long leg, you can figure out the short leg. But what are we going to have to do? Yeah, good. We're going to have to take the long leg and divide it by radical 3. Which we can't leave like this, can we? So we have to simplify it. Okay, so this is going to be 10 radical 3 over 3. 10 radical 3 over 3. That's the short leg. And then this is going to be a little bit weird for you. What's the hypotenuse going to be? How do we double that? How do we take 10 radical 3 over 3 and double it? Who's going to be brave? Say it really loud. No one has an idea? What? Oh, 20 radical 3. Yeah, it's just double. If you multiply it by 2, see, it's okay to multiply the 10 by the 2. Multiplication is commutative. We don't have to go 10 times radical 3 first. We can go 10 times 2 first. So 20 radical 3 over 3. Kind of make sure 20 and 3 don't reduce down, do they? Okay, so there it is. So these are our two special right triangles. You'll notice I have a poster back here on the back wall, don't I? It's been up here all year. I think somebody made that for extra credit. Okay, so we have the 45, 45, 90. Legs are x. Hypotenuse is x times radical 2. And the 30, 60, 90. Short leg is x. The hypotenuse is 2x. And the long leg is x radical 3. Okay? It's worth it to know these. We see them often enough. And here's the thing. We just did ACT prep for the juniors, right? What's one of the things we talked about in ACT prep? Special right triangles. I talked to the kids after the ACT prep. Guess what? There was one of each of these on there. Now you could figure them out another way other than using this method right here. But the answers weren't decimal answers or anything. The answers were written this way, like 8 radical 2. And if you know that they're special right triangles, you're going to be able to figure out which one is the correct answer in about 5 seconds. If you don't know special right triangles, it's going to take you a couple of minutes. And one of the big things on the ACT is how much time it takes you. Will you have enough time to do every problem before you get to the end and just have to mark all C's or whatever, right? If you get to the end of the ACT and you have to mark a whole bunch of C's for the last 20 questions, it's going to be bad, isn't it? Okay, so special right triangles. Okay, so class is about over, isn't it?
Yeah.
All right. So I'm just going to let your brains fester on this overnight, and then we'll kind of review quickly tomorrow and do some work.